This is periodic properties of the elements. A journey across the periodic table is like a journey through chemistry, which might be the corniest thing I've said at least this week. All right. Periodic table is organized in a particular fashion, and that organization is important because it highlights some of the physical and chemical properties of the elements. They can be in periods, which goes across the row, or down the column, which we call a group. The shape of the table can be explained by the orbital model. So this is the idea that the S orbital has two groups and they have two valence electrons. Same with the p orbital that has 6 groups, etc. and can hold 6 valence electrons and so on. We talked a bit in class about effective nuclear charge and having to use this concept, the concept of effective nuclear charge, which is abbreviated Z with a little EFF subscript, using effective nuclear charge to explain the trends that we see in the periodic table. And effective nuclear charge is essentially the attraction between the negatively charged electrons and the positively charged nucleus. Like a magnet, negative and positive are attracted together. And the effective nuclear charge is basically the charge between the outer valence the attraction between the outer valence electrons and the inner positively charged nucleus. Now, one of the things that happens as elements get bigger and you add shells and shells of electrons, they actually have an impact on the overall effective nuclear charge. So the farther away the electrons get from the nucleus, the smaller the effective nuclear charge gets. In addition, the more electrons that are in the way of the outer valence electrons, the smaller the effective nuclear charge gets. And this idea is the shielding effect, and that's essentially the reduction in effective nuclear charge because other electrons not only are blocking the outer valence electrons from being attracted to the positively charged nucleus, but the shielding effect also is when electrons themselves are repelling each other. Both of these things will reduce effective nuclear charge. The basic way that effective nuclear charge can be calculated, which is not something you're going to have to do, but is an interesting idea, is, and again, this is showing you the Z with a subscripted EFF. That is the abbreviation for effective nuclear charge. The way that you would calculate this is by taking the atomic number and subtracting the screening constant. And that screening constant, at least for the smaller elements, is typically equal to the number of core electrons. So if we were to have sodium, sodium has 11 as its atomic number and 10 as the number of core electrons, right? It has 11 electrons, but 10 of them are core and one of them is a valence. So 11 minus 10 will give you an effective nuclear charge of +1. The shielding picture helps explain a lot of observations that we make when we're thinking about the periodic table. And one thing that's important is that the effective nuclear charge will increase as you move horizontally across the periodic table. And this is because these elements have the same amount of shielding and thus then the same nuclear charge. The effective nuclear charge will increase slightly down a family because the larger electron cores are less able to screen the outer electrons from the nuclear charge. But it's not quite as significant as when you move across a row. So let's move on and talk about some of these periodic trends and how they relate to effective nuclear charge. The first one is the atomic radius. The definition of atomic radius is half the distance between the nuclei of two like atoms in a diatomic molecule. And what you can see with atomic radius is that it basically decreases as you move across a period and increases as you move down a group. Now, how would you explain this as it relates to effective nuclear charge? Well, let's start with moving down a group. So atomic radius increases as you move down a group. Why would that be? Well, you have more electrons in the principal energy level, which means the atomic size increases. So when you increase the number of energy levels, you're increasing the distance over which the nucleus has to pull, and therefore reduces the attractions for those electrons. Also, there is some effect of the fuller energy levels providing some shielding between the nucleus and the valence electrons. So when that shielding occurs, the outer valence electrons are able to move farther away from the positively charged nucleus, so that atomic radius itself gets bigger. Now, the atomic radius also decreases as we move across a period. How would you explain that? Well, the electrons increase, but so do the protons. This increase in nuclear charge actually pulls the electrons closer to the nucleus, so the atomic size decreases. The way that you would express that when we're talking about effective nuclear charge is you would say that the effective nuclear charge increases the attraction of the nucleus and therefore pulls the electron cloud closer to the nucleus, resulting in a smaller atomic radius. One other note when it comes to atomic radius, and that's that the size trend in periods is less pronounced than in groups, and this is because of that shielding effect. A lot of times you might be presented with a figure that looks like this, and you would want to explain those trends as we've talked about with effective nuclear charge. Next up is ionic radius. So what are ions? Well, ions are charged atoms, and those can be positively charged or negatively charged. The term for a positively charged ion is a cation. They form when an atom loses an electron, and then you have an anion, and those form when an atom gains an electron. And if we were to look at ionic radius here, you would see a few things. First off, just as an overall introduction to this figure, the purple circles, I guess, are the native element, so not the ion, and the red are then the cations, and the blue are the anions. So you can see a few things here. First off, the purple would be the same thing as the atomic radius, so you see the same trend in the purple where they decrease going across a period and increase going down a group. But you also should make a couple other observations. First off, that cations are smaller than the parent atoms. So let's take a closer zoom on that. So cations are smaller than the parent atoms. Why is that? Well, they're losing their valence electrons, so they lose their, and when they do this, they lose their valence shell, because we're talking about the first two groups. So cations formed by the metals on the left side of the periodic table. The size increases as you move down, right? They're smaller than the others because they're smaller than the native element because they have lost electrons, which makes it easier for the, but still have the same number of protons. So it's smaller because they've lost electrons, but also because the nucleus is able to pull in the remaining electrons closer. And it increases, cations increase as you go down for the same reason as atomic radius did, because you're increasing the number of energy levels. Anions are actually larger than their parent ions. How would you explain that? Well, you're adding extra electrons to the anion, and so when you do so, you're not in addition adding extra protons, so the effective nuclear charge in this case is less for the increase in the number of electrons. So the effective nuclear charge, meaning that the force between the negatively charged electrons and the positively charged nucleus, is not able to pull them in as much as it would without those extra electrons. This size increases as you move down a group for the same reason, because you're increasing energy levels. And it decreases as you move across. Cations get smaller as you move from left to right. and so do anions as you move from left to right. This is because you are able, same reason with atomic radius, the increased nuclear charge can pull the electrons closer. Next up is ionization energy. The definition of ionization energy is the energy needed to remove an electron from an atom. And another way that you can look at ionization energy is the energy needed to overcome the attraction of nuclear charge and remove the electron. So let's look at a figure that we should be familiar with at this point. This is looking at successive ionization energies, meaning ionization energy 1 is removing the first electron, 2 is moving the second electron, and so on for a bunch of elements. And one of the main things to notice here is that once you start trying to remove the core electrons, that's non-valence shell electrons, there's always a giant increase in ionization energy. There are some factors that affect ionization energy. The first is the atomic radius. Smaller atoms are able to really hang on to those valence electrons more tightly, so they have a higher ionization energy, right? Those valence electrons in smaller atoms are closer to the positively charged nucleus, and so that attraction between the electrons and the nucleus is stronger, so it's harder to remove one of those electrons than it would be for a larger element where the electrons are much farther away from the nucleus. Another thing that affects ionization energy is charge. The higher the positive charge becomes, meaning the successive electrons that you've removed, increases the positive charge on the ion, and that makes it more difficult to pull away additional electrons. So the idea is that the second ionization energy is always higher than the first ionization energy. But we know that it's not always quite so simple. The orbital type does play a role. It's much easier to remove electrons from p orbitals than it is from s orbitals, and that has to do with the shape. And it turns out that s orbitals tend to be closer to the nucleus than the p orbitals do. But as we talked about, electron pairing also plays a role. So within a subshell, paired electrons are actually easier to remove than unpaired electrons. And this is because of that repulsion that occurs between electrons, which weakens the effective nuclear charge, making it easier to pull the electron away. So you would typically think that the ionization energy of sulfur would be higher than the ionization of phosphorus, but because this electron is paired in the p orbital, it's actually easier to pull that electron away than it is to pull the p subshell or electron from phosphorus. This is the same idea of what I just explained, although written out. So this is another example. You would expect oxygen to have a higher ionization energy than nitrogen. However, nitrogen, the ionization energy is 1402, and oxygen is 1314. So nitrogen has a higher ionization energy, even though you would expect oxygen to. And the reason this is because it's easier to take an electron away from oxygen because of that paired 2p electron. This is just another way to look at it. This might be a type of graph that you would have to explain according to ionization energies. Just as another note, third, fourth, as you go, ionization energies, it takes more energy. And how much depends on where those electrons are located. Finally, we have electronegativity. Electronegativity, the definition is the ability of an atom to attract electrons towards itself in a chemical bond. One thing there's a lot of things that are important about electronegativity, but something to keep in mind is that the difference between the electronegativity of two atoms determines what type of bond they form. So it's an important thing to have an understanding. Electronegativity will increase going from left to right across the periodic table. Fluorine has the highest electronegativity, and if you can just remember that one, it's a little easier to think about the trends of electronegativity. So fluorine has a high nuclear charge and it's also quite small, and that makes it able to hold on to those electrons more tightly than any other element. Lithium, on the other hand, has a lower nuclear charge because it has less protons and is actually larger than fluorine, so it cannot hold on to those electrons as well. A way you would explain this with effective nuclear charge is you would say that effective nuclear charge increases the attraction of the nucleus and therefore strengthens the attractions for those electrons. So fluorine has a higher effective nuclear charge than lithium does. For groups, electronegativity will decrease as you move down. The bonding electrons are farther away from the nucleus the more you move down the periodic table. The increased number of energy levels increases the distance over which the nucleus must pull, therefore it reduces the attractions for those electrons. Additionally, full energy levels will provide some shielding between the nucleus and the valence electrons, which also weakens the effective nuclear charge. One thing that's important to keep in mind is that only full energy levels, not full sublevels, are a concern when we're thinking about shielding. I said that electronegativity was the last one, but I actually want to also mention quickly electron affinity, because this is where some people start to get a little confused. The electron affinity is the measure of the energy that's absorbed when an electron is added to a neutral atom to form a negative ion. Most elements are going to have a negative electron affinity, meaning it doesn't require energy to get that electron. Instead, once they get that electron, they actually release energy. The more negative the affinity, the more stable the ion is. And so here we have a picture of the affinities, and it is basically the exact opposite of ionization energy. And that would be the end of the periodic trends that we need to talk about.